So in class, when I introduced magnetism, we went through a lot of the conceptual things. We didn't really work very much with the equations and mathematical models. So I wanted to go through those here. So to start with, we'll do this side first. That's the order that the slides are in. So the force on a particle. So if we have a particle with charge Q, speed V, in a magnetic field with a strength B. So capital B is the strength of the magnetic field. The force on that particle depends on Q, V, and B, and also the sine of the angle. And that sine is the angle between V and B, the vectors V and B. So the force on the particle, and again this is just the magnitude, is QVB sine theta. So if the particle is going the same direction as the field, then that angle is actually 0. So the force goes to 0 as the particle goes parallel to the field. So that's the force on the particle. If you have a wire is essentially a whole bunch of charges traveling together. So a bunch of these Q's traveling together through a wire. You take QV, and that becomes replaced with I, the current, times L, the length of the wire. So L is the length of the wire. I is the current in the wire. B is the magnetic field that the wire is in. And then this theta is now the angle between I and B. Oops. The theta is between I and B. And again, this gives you the magnitude of the force. To figure out the direction of the force, you have to use the right-hand rule. So this gives you the magnitude only. This radius of curvature, if a particle goes into a uniform magnetic field, then when it enters that field, it will start to move in an arc. So it will go in a circular shape, and the radius of curvature of that circle is set by this. So it's the mass of the particle times the speed of the particle divided by the charge of the particle times the magnetic field that it's entered. And again, this is a magnitude. R can be a vector. In this case, R is just the radius, it's the distance. To figure out whether this thing's going to curve this way or the other way, again, you have to use the right-hand rule, figure out what direction the force is going to be, and then you can figure out how to draw this radius in there. When you put a wire loop into a magnetic field, what's going to happen, we saw this in class, if you've got a rectangular loop, then you're going to get a force in one direction on one side of the loop, in another direction on the other side of the loop, and the result will be that if I force down on one side, up on one side, it will create a torque. So this is the amount of torque that's generated in the wire loop. So in this, we have N. That's the number of loops. So if you have just a single loop of wire, N equals 1. If you have a stack of 50 loops that all, they're all the same, all laid one on top of the other, 50 of them, then you'd use N equals 50. I is the current through each loop, A is the area of each loop, and B is the magnetic field that it's in. This theta is now the theta between the area and the magnetic field. So the normal vector to the area between A and B. So for example, if I have a loop this is supposed to be three-dimensionally drawn in the plane here, the A vector sticks out from that. So that would be like the A vector when you're trying to figure out what this is. It's the same thing that we did with electric flux. You have to use the area vector is the normal vector of the loop. Okay. Magnetic field created by a wire. This is if you have a long straight wire with a current I flowing through it. The magnetic field created by that is mu naught. This is a constant. It's in those the front and back sheets of Walker. So mu naught is a constant similar to epsilon naught times the current divided by 2 pi times the radius. That radius is the distance from the wire. So that is the strength of the magnetic field. Notice there's no vector over it. So again, this is the magnitude or the strength of the magnetic field created by a long current carrying wire. If you take wires and wrap them into a long coil, that coil is called a solenoid. And a magnetic field is created inside a solenoid. It's a constant field. It's almost exactly the same equation. Mu naught. N is the number of loops in the solenoid. I is the current in the solenoid. And L is the length of the solenoid. So length of solenoid. N is number of turns or number of loops of the wire. Number of turns or number of loops. So those are the mathematical models.